Well, good morning, folks. I think I'll go ahead and get started here. Let me open us up in prayer and I'll give you a sense of what we're going to be covering. Dear Heavenly Father, Lord, thank you for the chance to work with each of the students in this course. I pray that the material will be clear, that every time we communicate in this course, that they'll see how it's adding to the skills that they're going to be needing and being able to utilize in their future profession. Pray that you would help them in their spiritual formation, Lord, that you would help them to understand the richness of scripture that they're getting exposed to with APU, the theological concepts in which we want to be drawing from that. Give them interesting and creative ways for faith integration in their future. In Jesus' name we pray. Amen. Okay, as is typically the case for Thursday, I'm trying to have it be more of a lab environment. But I'm going to spend a little bit of time going over some lecture material just to give a little bit of context for some of the stuff that we have been getting a chance to be exposed to. And so we've been talking about computer arithmetic. And so since this can get a little bit complicated, what you're seeing is that we go use our computers, it's all fairly straightforward. But then when you start to dig into the depths of the architecture, as far as you want to go, there's a lot of details that are interesting and at times challenging for us to get a chance to get our arms around. So the things that we spoke about on Tuesday is we started to, first of all, get an introduction to the things that are here for computer arithmetic. We have these various ways of having representation, sign magnitude, twos, complement representation, and that's something I'll spend a little bit more time going over today. I'll show you an example of a digital circuit that does a full adder. I think in the next chapter we'll get another exposure to that, but this will be with a emulator tool that you'll get a chance to be seeing that. And then I'll just start to get a little bit into adding and subtraction, and then I'll keep the multiplication division for stuff that we'll be covering next Tuesday. But just wanted to give a little bit of a sense about that. I mentioned this workhorse that's found in computers, the arithmetic logic unit. Basically, everything gets routed to the ALU to process, and so that's going to be a key thing. It's like the Swiss Army knife of the CPU. And so there's inputs that are coming in, telling it what to do. The registers that it needs to be know that the information is routed to the ALU. Any flags that come out like an overflow, and that's not necessarily a bad thing. It just means that it's outside the range of what it can handle individually, and so there needs to be a way of dealing with it, and then having the results put in the registers. So then we had this chart where we spoke about, and so this is for 4 binary digits, and so we can go from +8 to -8, but really you can't do both. You can't have +8 and -8 with this, and so that's one of the decisions that have to be made. And so what we have here is an example for the twos complement representation. You can have a -8, but you can't have a +8. And when we get into a couple just quick sample problems here, you'll see what I mean. So this is like a table where you can relate the numbers that are in binary to the values that they correspond in decimal that we're familiar with. And so this just gives you a sense of that here. And so here on this here, we have like a negative number. And so we started to talk about this, some ways of converting numbers. And so when you have this is, if you have, this means you have a negative component at 128, and then you add these other things. You add a negative number to positive numbers to get a result. So this is just a little bit of a perspective for an 8-bit perspective of having the most significant bit of giving it some meaning. Well, we talked about a lot of this, and so how do we take the negation? We do a bitwise complement. So wherever there's a one, there's a zero. Whenever there's a zero, there's a one, and you add it. And so you go from plus 18 to minus 18, this example. If you wanted to revert it back, you can just do the same thing. You do a bitwise complement and you add one. So that's something that we can get a chance to be seeing. And so here we see how we can be doing if we're going to be adding a negative number to a positive number and figuring out what the result. So let's go back to the two's complement table for a second. And so here we have minus 7 as 1, 0, 0, 1. Minus 7 is 1, 0, 0, 1. And so just to be pointing out here, we're using this two's complement representation to help us do a calculation. And so then we just have to add the numbers, and fortunately everything works out. We get a result, and so we can go back to our table. This would be one way to do it. If you look up 1, 1, 1, 0, that's minus 2. And so here we can see that we're getting some further insight into this operation. There are a couple cases where we have to be careful of, and if we get this overflow. So what is 1, 0, 0, 1 and 2's complement? Well, going back to our table again, 1, 0, 0, 1 is minus 7. And so is that the right value that we want here? Well, if we just add 5 and 4, it should be 9, which we can't get. So this is an overflow. And so this is like an example. If we plug this into an ALU, that we would get a flag that would be coming out. So these are the kind of things that we get a chance to be seeing, that we can be starting to get some greater insight into addition and subtraction. So basically, subtraction is just with a slight caveat, it's the same as addition, as we saw here. We just take the two's complement, and then we can just do an addition. So that actually is one of the things that can help us. We talked about this before. Two numbers are added and they are both positive or both negative, then overflow occurs if and only if the result has the opposite sign. And I showed you an example of that. So that's some of the insight that I wanted to be sharing with you. Here are just some other examples that are just giving us more information, as I was trying to explain in the previous example. And so if we have a negative 7, we take the two's complement. And so we start with 7, and then we derive the two's complement. And so that's how what we use here. And so this is just giving some more details for those kind of cases. So that's what I wanted to share in terms of the next little snippet for the things that we're covering in the main lecture. Any questions on that? Okay, well, let me show you this was the, it's not the one that we're currently using, but it's the legacy one. And since I actually had a full adder here, I'm just going to go ahead and use this. And so I have the simulation button going, and I could easily do this with our new emulator, but since I already had this and I'm trying to show a couple of things, I didn't actually recode it in. And so what a full adder means, you can see that in a truth table for two inputs, either they're both 0, the output is 0. If one of the inputs is 1, then the output would be 1. But if you actually get them both to be 1, it actually gives this overflow situation. And this is where you need to have this carry over bit. And the difference between a half adder and a full adder is that a full adder deals with this overflow both in the input. And so this could be aggregated together. And so basically we have three inputs. And so let's just go through that logic. And so this is operational. So if I just click one of those, it'll give the output as 1. If I deselect that one and select the other one, we also get it that it would be 1. If they're both positive, then we see that there's a carryover that we need to be concerned about. Okay, well, let's give another situation. Let's say that we're having input that we're carrying from another thing. So that automatically says that we have this. So if I have another one, what that does, it says that, well, I have to deal with that. And so I get a carryover, but not the this particular element here. And then finally, we have the case where you can have both of them are positive. You have the carry input is positive, and then you get a result of both of these lights being lit. So this just gives you another reminder that everything that we're doing, we think of the capability of an ALU, you can break it down into digital logic. And so like what we have for this generic figure here of an ALU, we can see how it would start to work in various situations. This is a dedicated circuit for an adder. We'd have to have some other more complicated control logic to capture the programmability that is part of the ALU. And so, like, as we're getting into our assembly language part of the course, some of you may want to be doing a logical and or an or, comparing registers and then giving a response. Those are the kind of things that we'll be doing on that front. So that's the next little snippet that I wanted to get a chance to convey with you all. So any questions on that? Either thumbs up or just give me some feedback that you guys are tracking.
I'm good.
Okay, sounds good. So that's kind of reaching back a little bit from project 1, but thinking in the context of where we're going. There is another thing that I'll share, and this is still kind of straddling between those two, but here is actually a spec sheet for a part. It's for a memory device that's made by National Semiconductor. And they have like these multiple names, but basically you can be focusing on this 189. And there's two main classes. There's a 54-189, which means that it's more robustly designed. And so for military applications, a lot of times they would have either a 54 or a 74. A 74 would be for commercial. It's not as robustly designed. So maybe some harsh environments that may not work as well, but those are the things that we're looking at. And so I'll get to this in a minute, but this is another emulator for this circuit that I have that I'll focus on in a minute. So let me go down to the block diagram for this, which is probably a little bit easier for us to comprehend. And so basically this is a memory. And so it is a RAM, a random access memory chip, a 4-bit chip, where I have 4 inputs. And so I can select a memory element here, and I can either store a memory element there. So here would be the data inputs, and so we can write to this memory, or given an address bit, depending on the control logic, we can have that come out. And so that's what this is doing. And so you can see that these numbers are here. So this is giving a chance for us to see some of the steps that would go from taking a conceptual type of part and make it real and start to figure out how you're going to use it. These are the timing relationships where it takes a certain amount of time for it to go from a high state to a low state, or from a low state to a high state. So these are things that if you were actually building hardware that you would be considering. Now, I'm not going to go over that. That's out of scope for what we're trying to cover in this course. But here is another view of this chip. And so this is organized in the chip container. And so it actually has 16 wires that come out of this chip. And so what I've tried to do is color code the inputs and the outputs. There's a couple other things that you need. You need to have power and ground. And there's also the chip enable, so, and the read write. And so if you're going to write to it, so change the memory, you're going to have to enable that one. And if you want to actually be doing queries to this chip, you need to have it enabled. So this is an illustration of what that would look like, and a term that maybe you might remember, we covered it a couple weeks ago. And so you have a read-only memory, and then with the P, it's programmable read-only memory. And then with these other conventions, the EE, it's electronically programmable read-only memory. And EE it's a little bit more accessible in terms that you can make it more easier for you to be updating that information. So these pin numbers agree to what I was just showing here with this data sheets. And I'm not going to go through this in detail at this moment. But if I select things in a proper fashion, I can see that I can get the input out. And so when I click this positive, it's the inversion, and that's what that line on top of it means. It means that it's write enable, so I could write to that. That's what that means. And this other one is whether it is actually active to read information in. So here is the data that's being in that I would be loading into this EEPROM. Here is the addressing screen where I'm either going to put it into a specific memory location, or I want to read that information out, and it would be put out here to the output. So just trying to give you another sense of what we're trying to accomplish with our projects, get exposed to different parts of a computer architecture. And so those are some of the things that are helpful to give us a sense of that. So let's now focus on what we're doing with the Mars MIP emulator. I have been looking at what VS Code can do. And so the latest, what I've figured out is that with VS Code, so I'm running on an Intel 86 box. And so I can actually do assembly code using that, but the Mars MIP, it's not a complete package that I have been able to find that's within VS Code. And so this is what I was thinking could be the case, but there are some things that are available for ARM. Say if you just want to have an editor that would give you the feedback that you're actually putting in the proper format, but to actually run it so that you can be doing that emulation, that is not something that I found a way to be doing it in a complete IDE the way that we have with the emulator that we're using. So it is old, and I'm still looking for a replacement, but I just wanted to give a little bit of context there. So I know a couple folks were thinking about what they wanted to do with their Mars project, and things that I've heard was like trying to mimic what we did with the digital logic circuits. And so you're going to be focusing on the OR and logical AND functions. And what I'm going to do today is to walk through another program And so the focus of this is it has a function and it's using the stack. And so a function, you can actually do that in assembly language. And so it's basically what you're doing is you're going to another sub area of your code here, and we'll get to that in a minute. So the first thing that we always want to do is we want to assemble it. We have mentioned already that one step that happens here, it can take the lines of code here and expand it into multiple lines. And so it breaks it down a couple of times into multiple steps. And that's what we'll get a chance to be looking at here in more detail. But so the big thing that you're doing is you either define variables and you stick values in it, or you just directly work with registers. And so here we have, we initialize the registers with some values. And so we have X and Y, so we have to be defining X and Y somewhere. So here in the data section, we're having X is 5 and Y is 0. So we can actually use variables, but before it hits the CPU, it actually is going to convert those to numbers that it can actually do something with it. It can't process a reference. It has to place the information from that reference and do that. So let me go ahead and open up the command, because they're the command summary. And so we have one command. So we have LW load word. So we load whatever we've set to be X into register S0. And then the same thing with Y. We now want to be calling a function. So if we're calling a function, it means that we need to be storing stuff on the stack. That's what we're choosing to do here. And so and then we do this call. Let's look this up, JAL. So JAL and jump and link. And so this is the thing that we have. So we're jumping to this other, effectively a memory location. So when we get into seeing what it looks like when it's compiled, it's going to take us to another place, and then it's going to start executing what we have here with this label here, and it's going to do this. And so we adjust the stack pointer. And so this is this add immediate. And so this is where we use this value -4. So the add immediate is addition immediate with overflow. So that's what we're doing here. We have the SW command. So it's a store the word. So these are, you can see how when you're writing code in assembly, everything is atomized, and so it's at a lower level. So this function overwrites S0 and S1, and so we should save those on the stack. And this is a quote pushing onto the stack in terms of giving you an idea. So we adjust the stack pointer again, and then we save S1. And so then we do the function math. And so what this function is trying to do, so it's a function, it deals with integers, returns a value stored in V0. The return address is stored in RA, put there by the JAL, the jump instruction. And that's the basis of what we're doing. So we're doing some additions, putting information on the stack. Let's look at this other command here. So this is, we have some more complicated math, not just doing additions. And so MUL. So MUL is a multiplication without overflow. So you can actually do multiplications here in assembly language. So 2 times 2 is 4, 2 times 3 is 6, and so whatever it might be. And so now we're doing a multiplication of information in registers. Then we're adding, so 3 times A plus 5 is what we're doing here in the final thing. So we're initially we put 3 into a register. Then we do this 3 times that value, and then store it into a register, and then we do add 5 to that results. We move the result to V0. And then before we do a return, we want to put everything back the way it was. And so this is that other things that you can almost think of this maybe as an interrupt per se. That's another way where we saw this kind of operation where you put things aside, you do what you're called upon to execute, and then return things back to the way they were when you were done. Then we have the JR command, and so JR is the jump register unconditionally, and so this means you just go right back to the pointer that is that's looking at RA. And so that's this register here. So we're using the naming convention for these registers, and so if you see anything with a $sign in front of it, it means that you're specifically talking about a register. Then so we can start to segment our code into functions if we so see that is a useful thing. So we did that manipulation, 3A plus, make sure I get it right. So 3A plus 5. So whatever kind of math operation we want to do, we can execute that. Then we can do a syscall. So let's remind ourselves what the syscall for is. Syscall for is a print string. So we print the message 1. Message 1 is Y equals. Then we have LF is a carriage return, a line feed. In case you're not familiar with LF, what that typically means. Then we print the result. So we printing an integer. So this is what this syscode 1 means rather than a string. So the syscall 4 is for printing a string. So we want to make that distinction. We print a string out, and then we print the new line. That's what we have with the line feed. And then we do a clean exit call with syscall 10. So I'll go ahead and run that program just to give you a sense of this. But we walked through it, and hopefully that would help to see what it is. So we have Y is equal to 20, and we get the line feed, and we get a nice clean termination as a result of that. Any questions or comments on that?
Does it work with decimal input?
That's where we're starting to get into our number representation. To be, the short answer is computers don't know how to deal with decimal points, and so you have to manage that the way that where you have the decimal point. And so in the last chapter, we were starting to look at that when we talk about the radix point. And so that's where having like scientific notation is a way of how you handle that. So effectively, like the whatever position the like the decimal point is all the way at the end or the other end, and then that's how you manage that with for decimal type of numbers that you're processing. That's a good question. So any other comments or questions that people have on that? Okay, I'm going to have us do a group exercise. And so what I'd like everybody to do is go ahead and open up your Mars emulator and then open up the program that I've shared in Canvas, the sample Hello World program. And I want you to make a copy of it. So don't delete your master, but make a copy and then have it print Hello APU. You can do something other than that if you like, but I just want you to get familiar with actually running and producing a result in the Mars emulator. And you can either just give me a thumbs up when you're done, or you can put it in the chat, whatever you'd like to do. Just give me some feedback on that, because I'd like you to begin to now start, especially in our lab time on Thursday, to have you do some of this coding and hopefully break the ice and make it easier for you to be doing some of this on your own. Everybody got your Mars emulator up and running?
Yeah.
Okay, so let me remind you where the file is located. And so it's in Canvas. So if you go to the home page and then if you go click on the project resource information, and then if you, so this is the project resource information tab. So going back to the main, and then go to the project resource information, then scroll down here to the example 2 _ hello _ world.asm. That's the one that you want to download. Okay, good. So we got a lot of folks saying that they got that to work. So hopefully that breaks the ice for you to be seeing how you would do that type of coding here. And then after that, it's beginning to start to manipulate that a little bit, having some more logic. So we have been exposed to a couple of different examples of doing some assembly language coding in the syntax that we have with the emulator. So here is one that we had last time. So I don't know if I can do this. Yeah, it doesn't let me to, well, maybe I can do it this way. See if this works. Okay, I did a copy and paste of a handful of lines of code that I have here for this project. If you want to copy and paste that, you could actually, even with that new assembly language program, put in some of those lines. And you can actually look at the manipulation that takes place here if you do the single step mode. That's one possibility. And give that a shot. So I'll give folks a minute or two, just give me some feedback. If you want to try adding some lines of code to that, give that a go. Since this has this line main, you're going to have to make sure that you have this global main. And I'll go ahead and open the hello world example. I think you probably already have it. Yeah, you already have that. So what you guys did is you changed this message. And now what I'm having you think about is you can think of where, if you wanted to put a couple extra lines of code for like what I was showing you. Here, where would I start to be doing this? And so, David, this isn't doing the logical and or, but it's giving you a chance to see what it's like to manipulate registers. Dealing with registers, adding material, adding things together, and then storing it. Any comments or questions on that? People tracking what I was having you do? Give me a thumbs up, thumbs down. Okay. Let me just sample around a few more people. Isabel, any comments to that? Would that make sense? Ryan, that was a code stub. It's not a complete program. I was just giving you some sample lines that you could add to what we were doing already. So you could start to add a few lines of code in your modified hello world and see how that works. Okay, good. So Isabel, I'm glad you got that to work. So actually, when we start to kick the tires on the things that we're doing in our project work, hopefully you're seeing it's not too overwhelming. I don't intend it to be, but just incrementally educational as we move along, covering some material. Well, let me move on to the next area that I wanted to touch base on. And so this gets into the third project. And I briefly have talked about this, but I'm going to go into more detail on this one. And so this is using a special type of LED. LED stands for light emitting diode. And so by saying RGB, it actually has a red diode, a green diode, and a blue diode all built into that one device, which makes it kind of interesting. So this way of presenting the layout is probably complicated, but it's still actually telling you the information that you would need to actually put this together. And it shows you that there actually aren't that many devices that you need to make this work. So you have your Arduino Uno. I think almost everybody, I think Josiah had a slight variant that he didn't have an Uno. I've shown you that I've done a few things with an Arduino Nano. And so you need to make sure that you hook things up to the right pin. This is a schematic representation of a resistor. When you have this kind of thing with the triangle and a line, that stands for a diode. But if you have a triangle and a diode with these two arrows like that, that means that stands for an LED. And you can see the little R here, so that stands for R for red, G for green, B for blue. And you can see that we put in these resistors on each one of these things. And so a diode is really good at conducting in one direction and really bad at conducting in the other direction. So this is like if you didn't have this, it would be like turning on your water faucet full volume. And actually it would likely cause problems with your diode here. So this is one of the reasons why we put in a resistor and this funny looking Greek symbol here that stands for ohms. And so this means it's 220 ohms. So what we're actually doing, and so I know, David, I saw the size of yours, it was actually smaller, but you're going to have with your wiring board, this is how you start to hook things together. And you actually have exactly where you're going to be putting those items together. And so this is this LED that actually has 3 LEDs built into it. And so you have this G and D that stands for ground. And so you need to tie this pin here to ground. And let me go back a few charts because I think I shared it in here. Because you got to figure out which pin is which. And so this is this RGB LED. And if you look carefully, if you were to pull this out of your kit, and I think everybody has this in your kit, you have one lead that's really long, and then they go down from there in terms of size. And what this does, it helps give you the convention of which one is which that you're going to be connecting with which value. And so that's one thing. And here we have a convention here. You can see that one side of it has a little bit of a cutoff here, so it's not a complete circle. That's another way that you can get a sense of where you would be connecting this in this board. So it's a little bit harder to see here, but this first pin, and they actually, you have like these different wires, different colors. And so this one is red. So red goes to pin 6. And there is a convention for doing this, but if you look for a resistor that has brown, red, that's going to be 220 ohms. And another thing that you'll have, you can have like a package of resistors and also label it. So even if you don't even know that, you could easily get that figured out. The next one is a green one. And so you do the same thing. Each of these 2, 4, 5 pins are all wired together underneath. And so you could stick it in any one. You could stick it in this one. You could stick it in that one, this red wire. But just to make it easier, they're just showing it this way. And then for the blue LED within this RGB LED combo, we have the same thing. And that's all you have to do for the hardware. So this could be an example of one of your projects that actually would only take 4 wires, 3 resistors, and then 1 device that you're using. So let me pause for a second there and see if anybody is following what I showed here with the hardware portion. Thumbs up, thumbs down. Kyle, does that make sense? You're following what we're going through here?
Yeah, more or
Okay,
less.
good. So this is an example where sometimes the hardware side can be easier than the software side. And so I'll pull up um, my Arduino IDE in a second, but this is just a screen capture of some of those lines of code. This was another version of that. And this was an actual demo that I was showing, and I still have it wired up. I can pull it out, but the focus, what I'm trying to do now is just give you a basic orientation of how you do things. So as usual, you plug it into a USB port. That's how it gets its power. That's how you upload it to your Arduino. And then you need to have this wiring board. So this is like about the half of the size of the wiring board that is shown here. So you can get these white wiring boards in various sizes. And so that's just a quick synopsis of that. So, and this is the actual Arduino code for that. So what do you need to do? You need to define these pins. And so remember, with this schematic, we have this 6, 5, and 3. So we have 6, 5, and 3. 6 is red. 5 is green. And then 3 is blue. And this, what I'm showing you here is the very first Arduino kit that I got, the CD that came along with it actually had this sample program. And so this is something that should be fairly accessible for you to give you a basis for getting started. And so maybe you're going to have something like this. And this was, they also, for some of these projects, it would have a companion PDF. And so this is the thing that I was showing you, those 4 pins, that they're different lengths to give you an idea. So here, like the longest one is where you put the ground. And so that's what you have there. One of the things that the program that I'll talk about in a minute, how it changes from one color to another, it's something called the duty cycle. And you can see this, that if you only have it on, say, for 5% of the time, it's not going to be as bright as when it's on 50% or 90%. And so what they have, and you can see the schematics that I showed you, I put them in the PowerPoint to make that clear. That's the things that we have with that. And so this code is actually fairly rigorous in the fact that we go from having one of them having it be real reddish, and then real greenish, and then real bluish, and then you kind of go from one to another. This is something that's fairly involved. You don't need to do this fancy of a project, but it at least gives you an idea of what is the realm of possible with a relatively simple type of hardware component. So let me pause and see if anybody has any questions on what I just mentioned. Well, I know a couple of you, David and Isabel, I was hoping to make it a little bit easier for you to start using your kit and pull things out. And so if you want, you can either take a screen capture of this, or you can look on either your CD or wherever you got it. You should be able to download the contents of that CD from the manufacturer and get the equivalent of what was on that CD. But maybe I'll just take this as a class discussion point. Let's assume that you were given this as a basis, and how might you adapt this to serve what you would be trying to to do a design that reflects what you're trying to do with your project. Anybody have a comment on that? Does this work for you in some way? Maybe you might put in some extra logic. Maybe you start to assign meaning to one or more of these colors. I didn't have time to define another one that was simpler, that was just one LED learning. So you can have an LED that just turns on or turns off. So to give you an easy way to give you a sense of if something is true, say if you're doing some type of security system, or whether the output of your logic is actually true or false. Maybe there's several steps that you get to that. So let me see if anybody has any comments on that.
When putting the RGB lights together, can you also like put on the display screen as well that comes with the Arduino to say if it passed or failed? Is there a
Yeah.
way? Okay.
Yeah. I'm not going to run this. I don't have my Arduino hooked up, but what I can do is just to show you. So if I open the serial monitor, yeah, I don't know if it's going to allow me to do that or not, because I don't have it plugged in. Yeah, it's not going to let me do that. So I have some other examples that show that, but if people aren't catching what David is saying, a couple of weeks ago, I showed you an example where literally I just had the Arduino app through the USB hooked to an Arduino Uno with nothing else attached to it. And I was looking at the serial plotter, and there's two things that you have, either the serial plotter or the serial. So what David is saying is you could actually write to that serial monitor what it actually, querying your hardware, came up with some sense of what the status is. And so you have this cyber physical exchange, and then having a result that you put out.
On it.
Okay, sounds good.
Still on it. I don't see serial in your contacts. To who?
Oh, wow. I don't know why Siri decided that I'm saying something that wants to do something. So
To who?
amazing.
It's nice to be appreciated.
Let me see if I can figure out how to
Sounds
mute
like
it.
Y2K.
Okay, I guess AI is getting everywhere. Okay. Yeah, I think I got that to go away. So, yeah. So I think that's about what I was trying to cover. We touched a lot of different topics here with our lab time, and let's just do a quick round the room. Anybody have something they'd like to share what you're doing on your project? Say for your project 2 with your assembly language. Can I get some, either put in the chat or go off mute? What do you envision that you're going to be doing with your assembly language programming?
I did mine on like the calculation, so I did like multiplying adding and division, and then I was messing around with the loop function, so I was trying to understand that.
Okay. Good. Enzo, you want to give us a heads up on what you're envisioning that you're going to be doing with your assembly language programming?
Sorry, can you say that one more time?
What do you envision that you're going to be doing with your assembly language programming? We've been giving folks a heads up on how to do this. Just wanted to.
Oh, right, yeah. I don't know. I think it's gonna end up being kind of similar to what I did before for my other project. It's
Okay.
kind of just like a series of yes, no questions to kind of help the user determine like which movies to watch.
Mhm.
And I can take care of like manually inputting the movies and like figuring out the right path and all that. But basically, it's like yes, no questions, different inputs like that. Nothing too crazy because I'm not too familiar with like Mars MIPS and how to code and all that yet. So something simple like that.
Okay. Yeah, that sounds good. Austin, any comments or thoughts?
I was just planning to kind of expand on what I did before with my digital logic programs.
Okay. You want to just share what you did with your digital logic just to give other folks a sense of
Oh yeah. I wrote a few programs that like they you input like certain like aspects of like a bouldering wall and it'll tell you if it's like possible for like a beginner level to do. And have different things like different rock types, angles of the wall, stuff like that.
Mhm. Yeah, well, let me kind of take that a little bit, Austin. And I know Ryan was also mentioning he wasn't sure how to relate the Mars program. And so this is where you have to be thinking in terms of an abstraction. And so like Austin, what you're mentioning, like the angle of the wall. So it means that say you put into a register. A register is basically, from a Mars perspective, is the way that it communicates with the external world or other things. And so for the external world, you can say that what is the angle of the wall? 5 degrees, 10 degrees, whatever would be the kind of numbers that you would be looking for. You get that, and then you process a response to that. So maybe there's something that you have the command line that you query the user to submit, or you just hard code it. A lot of the sample programs that I've been sharing in class, it's hard coded into the program. But we did have, I do have an example for computing a Fibonacci sequence that I can show you where you get the input from the terminal. So let me mention Ryan's, and then I'll go to Isabel next. So Ryan is trying to figure out how to relate this to card games. And so basically you want to be thinking in terms of a high level abstraction of what would be an example of something you would want a processor to do fairly quickly. So I'm not an expert on a bunch of different card games. So whether it be poker or something, if you get a flush or something like that, I may not be using the right term. And so that would be one way. And so you're getting information and maybe giving a response. Well, if you have a flush, you have a high percentage chance that you're going to win. If you're playing 21, if you have like your total cards put into a numerical value or 17 or lower, it's maybe above a 50% chance that you can get another card and improve your overall attempt at trying to get to 21 without going above that. That might be something that you could be thinking about. So you also mentioned, can you make a stack? The code that I was sharing today was trying to give you an example of manipulating a stack, of using a stack, I should say. And so that is definitely something that you could do maybe you might want to be thinking about that. So let me just go with Ryan and see, does that help, Ryan, or do you have any follow-on things you want to put in the chat? I'll try and give a little bit more perspective based on that. Okay, well, I'll keep helping a little bit. You can send me an email. Some of you have done that, and I'm perfectly happy to get together with you to try and help fill in the gaps. And so let me know what might be the thing that's keeping you from figuring things out. And so Isabel is trying to simulate rock, paper, scissors. And so the thing that you would need is a random number generator. And so I believe there is something like that, but let's assume that there isn't. You could just kind of not have that and just say you have like a 10 numbers at random to say that you have generated with a random number generator and you hard code it. And so you have a sampling of 10 that you could then query. And so you sample the first one, and then next time you want to do a sample, you do the following one. And so you don't need to be proving the fact of how good it is an algorithm for doing a random number generator. So that would be how I would recommend to first of all start with that. And because the main thing is trying to give folks a better sense of how to be using the registers, doing some of the programming at a basic function level that you have when you're doing things in assembly language. Does that help, Isabel? Yeah, give me some, either a thumbs up or write a little bit more in the chat. Okay, good. Anybody else want to give a snippet of what you're working on, and I can help you to frame it? You know, one of the things that one of you said is that you were having to produce your proposal before we did the course, and I know it seemed a little bit awkward, but and I also mentioned that's kind of the scenario of a way that work will be in the future. But we're trying to fill in the gaps as we go, and trying to think with the end in mind is partly what I'm trying to have us consider as we do this. Let me just check with Avery. Any comments or questions you want to share a little bit of what you're doing with your project too, and I can help you frame it if you need that.